Okay, so organic-inorganic hybrid polyoxometalate lubricant additives to engine oils. In operating a motor vehicle today, there is fuel losses of about 10% due to engine friction and an additional 5% due to drivetrain friction, which is the friction between the drive axles and the transmission. So in order to lower friction and reduce wear within such engine systems, there's efforts to for improved fuel efficiency. There's lubricant additives within engine oils to help with that. The concept of formulating lubricant additives to engine oils is nothing new. In around the 1930s, a retired attorney who had an interest in chemistry with the last name of Wynn developed and formulated his friction-proofing oil, which sponsored these three men who are three pioneers of NASCAR, the Flock brothers. The objective of my experiment was to synthesize organo-modified polyoxometalates with a CTAB surfactant, and then to characterize through X-ray diffraction and scanning electron microscopy, and then to formulate the oils so that they would stay suspended within so that the synthesis would stay suspended within the oil, and then finally to tribologically test for reduced friction and anti-wear properties within the engine system. Organo-modified polyoxometalates, or OPOMs for short, are transition metal oxide nanoclusters, and they are hydrophilic, meaning that they dissolve in polar solvents, and they form a Keegan-like structure, as seen here, with the middle inorganic core being, in this case, I used the POMs of silica tungstic acid, which has a silicon in it as the inorganic core with a -3 charge, and phosphotungstic acid, which has a -4 charge with phosphorus. So in this structure, the Keegan structure, the middle atom, the orange one seen in the structure, is the inorganic core. And then it's surrounded by oxygen atoms in red here, bonded to the transition metal tungsten. And then that is anionic. And so the CTAB surfactant is organic and it is cationic, which in the synthesis, it wraps around the inorganic core of the polyoxometalate anion. So synthesizing ratios, they vary from different percentages and percent concentrations of polyoxometalate to surfactant, ranging of 1 polyoxometalate to 1 to 20, 1 to 10 to 1 to 20 ratios. And the type of polyoxometalate used was varied between silica tungstic acid and phosphotungstic acid. And then we also added ammonium chloride salt to convert it from an acid to a base to see if that would have any effects on the anti-wear and friction properties as well. A total of 9 samples were synthesized in oil. And for non-disclosure purposes, the following slides will have numbers instead of actual letters instead of actual numbers. So as you can see here, the scanning electron microscopy images were all taken at 10 microns. And the first row is silica tungstic acid, which exhibits more of a sheet-like structure, and layered sheets are piled on top of each other. And then in adding the ammonium chloride salt, it caused it to ball up, which was not as desired. And then changing it from the inorganic core to phosphotungstic acid caused long structures, rectangular structures to form, which became very long and broke off. So that was not as desired as well. X-ray diffraction was done on the dry powders, and comparing the dry powder of silica tungstic acid to the following ratios, you can see that the silica tungstic acid is present within the products, and that is seen by around 10 for a 2 beta value. This early 2 beta value indicates a longer distance between the atoms, indicating that the CTAB surfactant is doing its job at preventing agglomeration of particles. Varying percent weight concentrations were used. However, they were all tested at a 1% weight concentration of OPOM surfactant in synthetic polyalpha olefin base 10 oil. Tribological testing was done, and tribology is the study of friction, lubrication, and wear, and particularly within engine systems. And that was done using this high-frequency reciprocating rig for 1 hour using a steel ball and flat in a back-and-forth motion. In hopes for a tribochemical film layer to form during testing, they can be either a low or high friction. In this project, it was of course desired that for low friction in order to improve fuel efficiency, etc. And they are thin and transparent, only 0 to 350 nanometers thick. And then they can give insulation within the steel ball and flat. So if it's fully insulated, you'll have a electrical conductivity value of around 0. However, if it's in full contact, if the steel ball is in full contact with the flat, you'll have an electrical conductivity value of around 0. However, if there is any insulation, that value will increase. And then for friction coefficients for an oil with a tribochemical film layer in it, they're around 0.03 to 0.15, and then the typical lubricant additive oil on the market today has a friction coefficient of around 0.11 to 0.15. And in changing the synthesis ratio, you can see that we actually found a oil that had one of the ratios exhibited very low friction, which is unseen for a lot of polyoxometalate lubricant additives today. So, and that was seen at a steady friction coefficient of around 0.05 throughout the duration of the 1 hour test. And then this is just changes in synthesis ratio. And then it's not just, this was using one particular inorganic core. And then it's not just the surfactant doing all the work that is seen, because this yellow one is just the synthetic oil plus the surfactant. So the polyoxometalate is also doing work within that. And then also changing the inorganic core from phosphotungstic acid to silicotungstic acid. Ratios D and E, which is seen in the green, and the red are of the same polyoxometalate core, and they were better than the other core ratios, which are the brown and yellow. And then we found that the larger polyoxometalate and surfactant ratio is better. Adding ammonium chloride salt, converting it from an acid to a base, actually was better for the smaller ratios, but it did not help for the larger ratios. And then this is just that one following through that one oil at that ratio that worked, that did not have ammonium chloride in it. And then repeatability of this one oil to make sure that it was not just a fluke experiment. The testing was repeated on the original oil that worked, and then a second and third synthesis was performed. It was found that the oil takes about a month to fully formulate, and my time at the lab was done before I could before the 1 month was over to formulate the oil. So that's why there's such varying results here. However, in due time, the friction coefficient should be around 0.05, but that just requires more testing. And then changing the percent weight of the concentration of that particular oil that worked, changing it from 0.05 to up to 2% weight in the oil, just to see if it had any effects, but the original 1% weight concentration was the one that worked best. And then electrical conductivity. This ratio E is the one that works for a lower friction coefficient, and that also is seen here with a value of electrical conductivity above 0, or yeah, in the beginning, and then it drips down to about 0, and then in the end it also rises again above 0. So that indicates a possible tribochemical film layer forming. And then wear scar images were taken using a measuring microscope at 20x magnification. And the larger the wear scar, the bigger the magnification, or the larger the wear scar means the worse the anti-wear property is. So the unmodified oil has a lot of discoloration, and a large wear scar. However, the oil that exhibited the low friction coefficient is ratio E. You can rarely see a wear scar on the flat at all, and a very small wear scar on the ball. So it also has good anti-wear properties as well as low friction. And then this is just taking that ball that was done on ratio E and seeing the volume lost within it, and there's barely any volume lost compared to the one with the unmodified oil. There's a lot of volume lost wear on the system. So it was found that this is just higher resolution scanning electron microscopy images of the ratio synthesized. And it's found that a layered structure of sheets work well as lubricant additives so that it provides better protection and possible tribochemical film formation. And then varying the percent weight concentration, varying the ratios, and the type of polyoxometalate used provides for future work for this project. And it's a promising field combining the fields of chemistry and tribology. Any questions?
Questions?
So you tested this with PAO. Do you think maybe in the future you might test it with ester-based oils?
Yeah, they could be if this one gets on the market, and yeah, definitely possibilities for that. Yeah, polyoxometates, they provide a lot of promising work, and not just this field, but others as well. So.
Can you say again if the layered structure is better for, or like with the help?
Yeah, this layered structure, as you can see, it's better than the phosphoglycolic acid in that it forms more of a layer and protection between the steel ball and the flat. So in forming a tribochemical film layer, it would just provide for better insulation and better anti-wear properties. And yeah, this is just a closer up view of it.
And I had one quick question.
Yeah.
So on the conductivity test, actually, you said the layer should insulate more, but you were also, with the additives, you might have been adding ions to the solution by doing acids or bases, and that would affect conductivity too, wouldn't it?
Yeah. So, yeah, there's a lot that goes into that. We're just there's a lot more than just saying that this exhibits a tribochemical film layer. There's a lot more tests that have to be done, and then also looking at the actual flat, you can do another. I think it's 4 years. You can do other and see if actual residue on the flat indicates that.
So it's possible you still have a layer and the conductivity doesn't suffer that much.
Yeah.
Any other questions? Okay, let's thank Ashley again.